let's have a look at 8.3, which is more trends in the properties of the elements in period 3. By this point, you're going to know about the structure of the periodic table. You're going to know where the S block, the D block, the F block and the P block are. You're going to know why scandium is not actually a transition metal, even though it's a D block element. You're going to know why zinc is not a transition element, even though it's a D block element. You're going to know why there was a bit of controversy of where to put hydrogen and helium in the periodic table. You're also going to start to know some of the trends in period 3 of the periodic table. So you're going to know the trend in melting points and boiling points of sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine and argon in period 3. You're going to know that phosphorus is P4, sulfur is S8. But we're going to look at now, the first thing we're going to look at in this lesson is we're going to look at atomic radii. And we'll stay on period 3 for this. We're going to look at the atomic radii of period 3. First thing though we're going to have to look at is what is actually meant by the word atomic radii. Okay. Radii is just plural. It means radiuses, if that makes sense. So let's have a look at what atomic radius actually is. Okay, right, let's draw an atom. Here is my atom. So we know that this particular atom has got 3 protons, therefore it must be lithium. And we might draw it like this. You'd have seen this sort of thing before. So you might think to yourself, well, okay then, right, atomic radii, well, it's just this distance here, isn't it? Centre of the atom to where the outer electrons are. It's not actually as straightforward as that. Yeah, it's not straightforward, it's just that distance there. The problem is, an atom really isn't this sort of structure at all, is it? What happens is, we have a higher electron density towards the nucleus, and that electron density gets less and less and less as it gets further away. So it's not really clear about where the edge of the atom actually is. It just kind of fades away, because the electrons we know now when we do A-level that they're not actually in specific places. So it's not exactly there is the edge of the atom. So what they actually do is they measure the distance between 2 atoms chemically bonded together. So I'll give you an example. So if we pick the most simple diatomic molecule, and that is H2, hydrogen, we know that each hydrogen atom has 1 proton. They don't have any neutrons, not that particular isotope anyway. And if they're chemically bonded together, what we get is we get 2 electrons shared here. So this one has now got a full shell because it has 2 electrons, and this one's got a full shell because it's got 2 electrons. So because the distance between the nucleus and the edge of the atom is really difficult to measure, we're doing it a different way. So what we do is we measure this distance from the centre of that nucleus all the way to the centre of that nucleus there. We measure that distance and we half it. So basically, we take that distance there and we half it. We divide it by 2, okay? And that gives us R, which is the atomic radii, okay? Or radius, okay? If there's only one of them. Okay, that works for things which are covalently bonded. There's a covalent bond there, so it works if it's covalently bonded. So what I'm not going to do in this particular lesson is tell you all about the atomic radius of any elements in period 0, because we know that they don't form covalent bonds. So if we're discussing period 3 today, the group 0 element in period 3 is argon. So you'll find that argon does not feature in this lesson. Okay, so I'm not going to give you any numbers for argon, because argon can't covalently bond. That's because it's got a full outer shell. Okay. Don't think I've just missed it off because I've forgotten about it. And the reason why I've missed it off is because you can't really measure it properly. All right. So let's have a look at the atomic radius across a period. Now, we're looking at period 3 here. I don't need to discuss every single element in period 3. All I'm going to do is I'm going to just discuss 3 elements in period 3, and you need to imagine that the trend is just going to continue. Okay, so I'm going to pick the first 3 elements in period 3. So we know that the first 3 elements in period 3 are sodium, magnesium, and aluminium. Let's write some information down about those 3 elements. We know that sodium has got an atomic number of 11, magnesium 12, and aluminium 13. The relative atomic mass at 23.0. Remember, we're in year 12 now. Don't forget that number after that decimal point. Magnesium is 24.3 and aluminium is 27.0. Obviously, the most common isotope of magnesium has 12 protons, 12 neutrons and 12 electrons, so a 24.0 if you like. We do have some magnesium atoms there which have an atomic mass of 25, hence the 24.3. Okay, so we can work out the number of protons, electrons and neutrons from those 3 atoms. So I'm going to just change that one here to 0, or what I could do is I could just put a line through that, a line through that, a line through that there, and just calculate the most common isotopes. So that's sodium 23, magnesium 24, aluminium 27. So I'm not going to write the word protons, neutrons, electrons. The quickest and easiest way to do this would be to just write P11 as in 11 protons. So increase the number of protons there. And we've got the number of neutrons. And the number of electrons for any atom is the same as the number of protons. Okay, nothing new there. Now, you might be inclined to say, okay, if we're looking at atomic radii, so essentially how big the atoms are, then we might think that this is the biggest, because it has a greater atomic mass and more protons. But actually, that's not the case. Out of these 3 here, this one is the smallest. This one is the largest. And in fact, if we went all the way along period 3, right the way to the likes of sulfur and chlorine, you'd find that their atomic radiuses are actually smaller. So as we go across a period, and this is for any period, the atomic radius actually decreases. Okay, there's one mark there, there's one fact. We need to explain that though. So let's have a look at the electron shells. Let's just stick with the GCSE electron arrangement for this particular question. It is sufficient. So we've got 11 electrons here. So that's 2 in the first shell, 8 in the second shell, and 1 in the last shell. So 281, 282, 283. We can see here that the number of shells stays the same. We have 3 shells here, 3 shells here, and 3 shells here. Because the number of shells stays the same, then the difference in size here between these 3 atoms mustn't have anything to do with the fact that we're adding a shell or taking a shell away, because we only have 3 shells. So it must be something to do with the nucleus. Now it's nothing to do with the neutrons, because neutrons have no charge. They're going to have no effect on those outer electrons at all. It is something to do, however, with the number of protons. We can see that the atomic radius decreases as we go across a period. And the reason why that is because the number of protons increases. So if you've got more positive charge in the nucleus, then there's a greater force of attraction between that nucleus and those outer electrons. Remember, the position of those outer electrons govern exactly how big those atoms are going to be. So if you've got more protons in the nucleus, that's a higher positive charge in the nucleus, therefore a greater attraction between that nucleus and the outer electrons, therefore pulling the electrons in closer, making the atoms much smaller. So as we go across a period, the atomic radius decreases because the number of protons increase, increasing the electrostatic attraction between the protons and the outer electrons, pulling the outer electrons in closer, decreasing that atomic radius. Okay, there's your full answer. The atomic radius decreases across a period, and this is because the number of protons increases whilst the number of shells stays the same. A greater positive charge in the nucleus means a greater electrostatic attraction with the electrons, pulling them closer to the nucleus. Okay, so if we pick any period, you find there's a decrease in atomic radius as we go across a period. Now let's have a look at the atomic radius down the group. Let's just pick group 1. I could pick any group, but we're going to pick group 1. So I have lithium, sodium, and potassium. Let's do the same as what we did before. 3 protons, 11 protons, 19 protons, 7, 23, 39. Let's work out the protons, the electrons, and the neutrons. And the electron arrangements. Okay, let's just draw the sizes. That one's the smallest, that one's a bit bigger, that one's bigger still. So we can see as we go down the group, the atomic radii increase. Okay, let's have a look at the number of protons. We can see that the number of protons increases. Now we saw across the period here that as the number of protons increased, the atomic radius decreased because there was a greater electrostatic attraction between the protons and the outer electrons. We can see here that the protons increase as well. However, down the group, the atomic radii increase. Therefore, the nuclear charge, which is basically the amount of positive charge you've got in the nucleus, so this one's got a nuclear charge of 19, the nuclear charge is not the most important factor here. So what I'm going to do is I'm going to start my answer by using the words despite increased nuclear charge. So because despite increased nuclear charge, okay, so because I've already written that down, there must be a most important another factor here, all right? And when we write the electron arrangements, it should be blatantly obvious here. This one's got 2 shells, this one's got 3 shells, and this one has got 4 shells. So despite increased nuclear charge, as we go down the group, the number of shells increases. Okay, so the number of shells increases, and that's what increases the atomic radii. So as you go down a group, the atomic radii increase. As you go across a period, the atomic radii decreases. So it's decreasing this way, but increasing that way there. So if I sketch a periodic table here, like this, there we go. It's a quick sketch of a periodic table. We know that we'll go down the group, they get bigger, and we'll go across a period, they get smaller. Therefore, the elements in this corner here, are the biggest. And the elements in this top right hand corner, rather over here, are the smallest. So the trend down the group is to do with the number of shells. However, when you're explaining an exam question going across a period, it is to do with the number of protons, because the number of shells actually stay the same. What you've got to be able to do is, you've got to be able to compare any 2 elements and then say why one is bigger than the other. That's what you have to do in an exam. Okay, so that's atomic radii. We're going to look at something called ionization energy now. Now, you've studied ionization energy in topic 1. So we're going to recap first of all to make sure that everyone is sure exactly what ionization energy is, and also that you can define ionization energy. We're going to look at the first ionization energy specifically today. So I'm going to write down an equation with element E, and you often see in textbooks element E. Now if you look at the periodic table, you won't find element E because there's no such thing as E, which is convenient because the first letter of element is E, and we can use the element E to represent any element. Okay, I didn't want to pick an element. I didn't want people to think that I had a favourite element, even though it is actually carbon. So we're going to use E today. Now, here is an equation for the first ionization energy of element E. And I want you to write this down. Okay? So, let's have a look at this. We can see here that we're removing an electron. So, ionization energies is all about removing an electron. This is the first ionization energy. So, we're removing the first electron from an element to make a unipositive, or a singularly positive, rather, ion. So uni means 1, singular means 1. You can use both of those words. So I'm removing an electron. So the first ionization is a measure of how much energy it requires to do that. Let's just recap a definition though for the first ionization energy from topic 1. So we're going to write it down and then I'm going to tell you where to get the marks from. Okay? It's not something that you might have to define within this particular topic, but when we are going over topics, it's useful to remind ourselves of them. Okay, that's the definition. So the ionization energy is the energy required to convert a mole of isolated gas atoms, so we'll use the state symbol G here, into a mole of singly positive charged gas ions. There we go. Remember, ionization energies are measured in kilojoules per mole. So it's not just the energy to remove one electron from one atom. That would be absolutely minute, wouldn't it? It's energy per mole. So we see our values in kilojoules per mole. Now we're going to have to put energy in to do that. That's because there's an electrostatic attraction between the positive nucleus and the negative electrons. So because we have to put energy in, ionization energies are always positive. They're always an endothermic process. What we're going to look at now is the trend in ionization energies across a period and down a group. So let's have a look at going across a period first of all. So we're going to pick our first three elements across a period. So our first element was sodium. Now sodium has got 11 protons in the nucleus, so I'm just going to write 11 plus there for sodium. It's got 3 shells, 1, 2, 3, and we've got magnesium. It's got 12 protons. It's also got 3 shells. Theoretically, I should draw that one slightly smaller than that one. Aluminium, it's got 13 protons and 3 shells again. And we can write down the electron arrangements of these if we want to. And the quickest and easiest way to do that is to spot the previous noble gas, which is neon in every case here, because these are all in the same period. And sodium is a group 1 element, so it ends in S1. Magnesium is a group 2 element, so it ends in S2. And aluminium is a group 3 element, so it ends in S2P1. And don't forget the 3's here, because it's in period 3. Now, when we're removing electrons, we're going to remove the outer electrons. This is the first ionization energy. So I'm not going to bother drawing the inner electrons here. We know there's 2 in the first shell and 8 in the second shell in each one of these. So this is 3s1, so there's 1 electron there that I'd have to remove. For the first ionization energy of magnesium, I could either remove that electron or I could remove that one. To be honest, it doesn't matter which one I remove because they're going to be the same. Aluminium is a little bit different, this one, because what we've got here is we've got 2 electrons in the S2 orbital and 1 electron in the P1 orbital. Now, this P1 orbital is going to be much easier to remove. That could be, let's say, the S2. This one could be the P1. This is where our GCC diagram kind of fall down. So it would be this electron that we're removing. So in each case, I'm removing that one, or that one, or that one really, or that one, or that one. Okay. So it's the energy required to remove these electrons. As we can clearly see here now, that as we go across a period, the number of protons increases. The number of protons increases, therefore the electrostatic attraction between that proton and the outer shell electron is going to increase. Therefore, more electrostatic attraction is going to require more energy for that electron. Therefore, the ionization energy is going to increase as we go across a period. So I have an increase in ionization energy, and that is because the number of protons increase. What I'd like to see is I'd like to see you write this in full sentences, just like I took the time to do that over here. To be honest, if you can answer this question, you can answer this one. Protons increases, therefore the nuclear charge increases. If there's a higher nuclear charge, there's an increased electrostatic attraction between the electrons and the nucleus. I'm going to repeat this one more. I want full sentences for this bit here that I'm writing in blue. And that will require more energy to remove that electron. So as we go across a period, the ionization energies increase. Right, okay, let's have a look at the ionization energy as we go down a group. So as we go down a group, so from lithium, sodium, potassium, it's going to get much easier to remove that electron. Just think about the reactions of lithium, sodium, potassium. Every time lithium, sodium, potassium react, what we're doing is we're removing this outer electron here. So how easy that electron is removed determines how reactive lithium, sodium, potassium is. We know that potassium is the most reactive out of those three because that electron there is further away from the nucleus and it's shielded more from the nucleus. So if that electron is easier to remove, then the ionization energy must be lower. So as we go down a group, the ionization energy decreases. So the ionization energy decreases going down a group. And that is to do with the number of shells are increasing. So there's more shells. If there's more shells, that means there's more shielding. The outer shell electron is shielded more from the nucleus. The outer shell electron is shielded more from the nucleus, therefore less energy is needed to remove it. Okay, we've had a look at two things this lesson. So we've had a look at atomic radii going across a period and down a group. We've had a look at ionization energy going across a period and down a group. Just to recap, as you go across the periodic table, the ionization energy increases. However, the atomic radius decreases for the same reason. As we go down a group, the atomic radii increase and the ionization energies decrease. Again, for the same reason.